Okay. Welcome guys to our first of two academic talk nights of this term. My name's Davide. I'm a third year physics student. I'm not talking. So today is going to be James Vandeleur and hopefully Clemens Ulrich. Basically how it's going to work is James is going to talk for a bit and then we're going to have a little interlude halfway through. Chance to eat, chat to your friends, or just chat to James or Clemens if they guys have any questions. I think we're gonna have questions at the end, so we have a big panel. James is gonna answer a bunch of the questions. Hopefully that's all good. So we'll start. It's it's a regular next time.
Sorry, when? Okay, hello. My name is James. I've met a good couple of you by now. Rest I've not. So I've just joined UNSW this year. I've come from Queensland, and I've started my PhD with this bloke, Dr. Michael Schmidt. So I have put up, this is basically our group here at UNSW. Charlie has not updated his picture, but he is there, so you can enjoy his beauty in the flesh. And Jordan is the one brave, honest student who put his picture on. So we're part of this broader Sydney CPPC, which is the Consortium for Particle Physics and Cosmology. The word consortium is important there because it can't be a center because that means something to the ARC, but anyway. So this is kind of just an ad for high energy particle physics at UNSW. You also spend a lot of time at UCID with UCID people, and it's a really nice group that we do together. I've also put up there Depan and Yvonne, who are people who work very close to the sort of things that Mikhail does, although not exactly the same. So if you kind of like what I talk about today, but you think, oh, I don't know whether I want to sit next to him, you can go work with him. Okay. So what is high energy physics theory? Because I'm not touching experiment. So basically it's particle physics. Okay, so we call particle physics high energy physics because in nature, it doesn't make sense to talk about a single particle except at very high energies, right? As soon as you start coming down in energy, things start to form bound states and condense, and that's when you go and talk to a condensed matter. So we deal with these very fundamental building blocks of nature, which is one of the big draws of high energy physics, at least in my opinion. You get to do a lot of arguments from first principle. It also kind of includes a bit of cosmology, which is more to do with sort of pheno is the word. That's meaning the phenomenology, of the early universe, looking at how the universe started and how it propagated things. I've included gravitational waves because it's all sort of in the same ballpark, and there's some interesting new measurements from gravitational waves, and we might be able to get a good few constraints on our high energy physics models from gravitational waves. So it's all sort of physics that we need to know. Of course, a part of that, you then have dark matter and energy, and a lot of that is shared with astronomers. But you will often hear of particle physicists talking about a dark sector and introducing a new dark particle and calculating what interactions it would have. And in general, we really struggle with many body calculations, just because our machinery is not set up very well to deal with that. I suppose in principle, you could deal with it, but it becomes very complicated very quickly, very computationally expensive. So Many body problems, again, you would go to maybe a condensed matter physicist, and they have a whole different set of tools to deal with that. Yes. Okay, speaking of tools, what tools do we use in high energy physics? Predominantly, we use quantum field theory. It's in fact, it's the most precisely tested theory in all of human history by like several orders of magnitude. I've forgotten the exact number, but it's pretty good. We of course need a bit of general relativity. And that's not directly our focus, but it's important to use it because often we can do like a quantum field theory in curved space-time and sort of bring the two together. And a bit of code is always helpful because even though we like to write things down on pen and paper most of the time, it eventually does become too hard to compute. Okay, so some things I find beautiful in high energy physics is all the symmetries and group theory. Wow. It's really cool. So one of my favorite bits of maths is Noether's theorem, which you may or may not have learned yet. It says for every continuous symmetry there exists a conserved quantity of charge, conserved charge. And this is true in very general terms. And what I think is the coolest is that conservation of momentum is a result of a symmetry under Lorentz boosts, which is just so amazing, right? All you have to do is you assert that physics is the same in every reference frame, and from that you deduce conservation of energy. I love field theories. The maths of field theories is really cool. It's a bit of a steep learning curve. Once you get it, it's great. So if you're struggling with that now, persevere. It's worth it. It's really beautiful. And sort of what I've touched on already, the simplicity of these first principles arguments, right? So we do make approximations and assumptions, but most of that's when we want to go and calculate something. But when we're developing our theory, the idea is that we don't want to make any approximations or assumptions, right? This is different to, say, a condensed matter theorist who would have to make a lot of approximations and assumptions because, you know, they're dealing with huge numbers, thermal numbers of particles. Which is not to slander condensed matter physicists. I have great respect for them. It's a trade-off, right? This side. Some things I find ugly in high energy physics. It's all perturbative. Okay, so there are no exact solutions. It's all Taylor series basically, which is functional, right? You can calculate whatever you want, whatever arbitrary precision you want, but it's not very beautiful because it doesn't really give you much insight into what's going on as opposed to just gives you the number. Okay, so I've asked this question, what makes high energy physics a science? Because often we get a lot of criticism, and a lot of quite valid criticism. So there's... yes, this quite famous line, one more collider, I still have pleased, which ties very well into this is chapter 7 of this book from 2016, Direct Experimental Evidence of String Theory. There is no direct experimental evidence of string theory. So I include this because I think in general in high energy theory, you sometimes get people who how shall I say this, get a bit of an air about them and think that this is somehow a better physics and a more pure physics, and you start getting these cyclic sort of philosophy arguments. And at the end of the day, we do still want to be doing science. And it's important to remember that physics is an experimental science. But we do have some experiment. So let's. Yeah, so evidence that we do have. So we have colliders that go up to about 1 teraelectron. And so colliders give us a scattering amplitude, is the term, which is basically if we take two particles and throw them really fast at each other, what do we expect to get out and what probabilities, what distribution. So most of QFT is built around calculating these scattering amplitudes. So that's probably our main one. We also have astroparticle detectors. So the big one here is neutrino experiments. So they build these usually deep underground to block out a whole bunch of noise from all the strongly, when I say strongly, the ionizing radiation, let's say, from the sun, right? All that boring QED stuff. We know that. We knew that 50 years ago. We want the neutrinos. And then they have these big vats of usually noble gases. And when a neutrino hits, you can try and detect it. But these are very rare events because neutrinos very weakly interact. We also have things like LIGO, and there's a new experiment, LISA. So if you don't know, LIGO stands for the Laser Interferometry Gravitational Observatory. And it is two big lasers, or laser beams. I think it's like 13 kilometers long. And so you send them down, they hit mirrors at the end, they come back. And then you measure their interferometry, so you measure the phase shift of the two light waves you've sent out. And then that lets you measure on the precision of whatever frequency they use. I think it's something like 1,000 nanometers. On that precision, you can measure stretching and compressing of the arms, which is how we measure gravitational waves. Okay, so LIGO is a ground-based one. This new one, LISA, is going to be satellites that they're going to send out into space. And it will be exactly the same thing, but just in space. And they'll just be much, much longer arms, like something like 25 million kilometers or something crazy like this. As I said, this is a exciting sort of new area for physics because, of course, we have this problem with colliders where every time we want to discover a new particle, it's another multinational effort. And gravitational waves just give us another way to put constraints on our high energy physics. We get a bit from astronomy. I mainly put that in there because I mentioned dark matter and dark energy before, which is their astronomy observations. There's also, we can get some constraints from atomic measurements. So this usually makes use of things like parity violation. So if you imagine you've got your electric dipole moment in an atom, and then if you flip your parity, you expect that to flip over. And the standard model is parity conserving for the most part. And so most of the standard model things are cancelled by that, which means you can be very sensitive to anything that's not in the standard model. And so these are experiments you can do on a tabletop with lasers, which is much more economical than one more collider, please, I swear. So our ultimate aim then is to come up with this so-called GUT, the Grand Unified Theory, can explain all of these observations. In principle, at least, because as I said before, it's all perturbative. So even if we had the theory to actually calculate something that's much more than 2 or 3 particles would be very computationally expensive. Yes, although there is a school of thought that says maybe going for this so-called GUT is not the right approach. Instead, we should go for something else. EFTs. That requires a strong Monty Python reference. It's not just a random foot, I swear. Anyway. At this point, questions about general high energy physics, if any. If not, that's all good too.
What are EFTs? Or are we getting to that?
We'll get to EFTs. We'll get to EFTs. Yes.
Do you work closely with experimentalists in terms of like working with like data that they get, or are you very separate from them? Is there any overlap at all?
So we use the data they get. I would say the overlap is not that strong. The experimentalists also tend to be a bit protective of their data, which is partly the theorist's fault, because theorists will come up with a model and they'll say, this is a great model, this is my baby, I've come up with it and it's great. And then they'll say, oh, now I need proof that it's right. And they'll go and get their hands on all the raw data, and then they'll do some botched job with the statistics and make a claim. And so experimentalists will often not release the raw data. They will do their own statistics, make sure the statistics are good, and then publish that. So there is the separation, but as I said, we always make sure that we do our theory, we calculate observables, and then we match that with experiment. At the end of the day, that's what we're doing.
Has Lisa already been launched? Like, is that a project, or is that something that's already in existence? And
I don't think it's been launched yet. If it has been launched, it was very recent. Do you?
I heard something about the aim for 2030.
Okay.
There you go.
Do you know if it will be in our orbit? Like, will it be like? Surely it has to be within a respective orbit, right? It can't just be free space.
No, I think the idea is they're going to shoot it out, and then it's just going to propagate away.
Let's see.
So we get data from it. I know, but
You can do different speeds. Like you can do radio station.
In the end, the actual calculations end up being perturbative.
yes.
In a sense, that's really, so it feels like, in a sense, it betrays like the motivating principles of simplicity and beauty, because you don't actually get that, right? Apart from the explanations, as in,
Yeah. So yes. Yes. So this, I understand your concern. This is the concern that I think most people working in this have. And it would be great if we had analytical solutions. Does it, it's not ideal. Does it break everything and take away the simplicity and beauty? I don't think so, because we can still write down the theory, and in principle, it implicitly defines what the wave function is. But we only do the perturbation when we want to get a number out to match with the experiment. And, you know, there's all sorts of philosophies about this. One of them is that maths is more man-made than we might think, and thus there's no reason that the universe should work in a way that is well described by our maths. I don't know how much I believe that. I tend to think if you burnt all the maths textbooks, then in 100 years it'd be back exactly the same way. But yeah, this is a philosophy thing, right? This is interpretation. At the end of the day, the numbers do work.
Is that inherent to science? Like, is an exact solution, do you think, ever possible, or are you dealing with irrationals that just can't be simplified in that sense? Like, does it always have to have an inherent Taylor series or some infinity that's involved?
Yeah, that's an interesting question. I think in our current formalism, yes.
Is it irrationals that's causing it? Like, is it just numbers that go on to infinity that you just need to approximate?
It's not so much irrationals. It's you get infinities in the calculation, yes, which come from when you want to take an inverse and do an integral over all momenta, but it's 1 on k, so then you get a zero problem. It's basically the heart of all the problems. So it's really poorly defined maths. Yeah, so I think to truly remove them, you would have to define your maths formalism behind it. For example, the path integral is not mathematically well defined. The path integral is okay. So if you've got two states, sort of quantum idea is that the system can evolve in every possible way between the two states, and they'll be weighted by a different probability. And the path integral is the maths of integrating over all of those states, right? So that thing is not mathematically well defined. It gives us good numbers that agree with real life, so we trust it.
So one thing that I've noticed, right, there's a lot of mentioning of things not actually being mathematically rigorously defined, yeah. For example, in the particle physics lectures, we cover a lot of things, a lot of content very fast. But often when we come across things like the Dirac equation or whatever, often what we say is this was what was found to be working, right? And often when we, for example, solve the Dirac equation and we find the U1 and U2 spinors, I think we say these actually give us information about spin half particles, right? I think often when I look at it, these feels like a very convenient interpretation, as in very quickly, as in for things, right? As in, and then dismissing all the others. I'm just wondering if, for example, someone practicing in the field, energy physics and in general QFT feels very rigorously defined, as in foundationally, as in, is it as in like just single parts that someone has, you know, trodden or walked? Like, we actually, is it a very solid foundation that's not really what interpretations?
No, it is. It is a very solid foundation. It is a very solid foundation. I think the difference. This is the key difference between physics and maths, is that when we say it's a solid foundation, we've built it up from observation, which is not what maths does, right? Math builds it up from some arbitrary axioms, and let's see what they're consistent with. So like quantum field theory is one of the areas of physics that has created a lot of maths, because there was a lot of maths we needed that hadn't been written down by mathematicians yet. But yes, no, it definitely is very rigorous. It is very rigorous. Okay. All right.
Actually, can I ask one more question?
Yes.
Going back to that thing where you said that some people get an air about particle physics being like pure and whatever. I just want to stir the pot a little bit. Do you have a least favorite type of physicist? I feel like I've got one.
I think I have
And I feel like everyone does.
Least favorite
Yeah.
type.
You can just say experimentalist if you don't.
Yeah. It's like we have 5 people.
No, this one's worse.
There's a particular type of physicist that
What a question.
that works a lot with pictures,
I know the one.
and
know the one.
I always think that.
Yeah.
I always think that's very phenomenological based. And I'm like, all right, anyway, we'll move on from that. There you go. The pot has been stirred.
Yeah.
The pot has been stirred. All right. So, what stuff do I actually work on? Ooh, let's get rid. All right. So we want EFTs. So these are effective field theories for neutrino mass models. Okay. So I'm going to cover first the anatomy of a field theory, then the standard model, which is just a big field theory. Then we'll specifically look at neutrinos in the standard model, and then we'll talk about how we can add mass to them. And then this 5 is where we get this effective field theories will come in, which is about physics at different energy scales. Okay. So a field theory is defined by a Lagrangian. Okay, and so anybody who's done classical mechanics will know that Lagrangian is kinetic energy minus potential energy. Okay. When this becomes a field theory, we write it like this. So this derivative term is the kinetic part, and this mass squared term is the potential part. Potential part. Let's just call it a mass term for now. Okay, it's the mass term. And then you do Euler-Lagrange equations of motion, and you get this is the Klein-Gordon equation. I think that should be a plus, actually, in the Klein-Gordon equation.
I feel like it should, yeah.
I think that should be a plus. Oh, well.
We know what you mean.
Oh, there it is. Okay, so then we can add to this Lagrangian a source term, this J, and when we do the equations of motion, we get a J here. Okay, this is just a classical source term that then propagates your wave. So we can then interpret this mass term as if it was an interaction. Okay, so when we go to the quantum field theory, this source term we represent as diagrams, and they represent interactions. Okay, so if our term here, say, if J was two other phi fields, then we'd get three phi fields, and we'd have an interaction of three phi particles, whatever phi is represented. Okay. So this is in QED. We have two electrons, the psi's, and we have one photon, which is that A field. Okay, so that's the interaction term for the base vertex in QED. Okay, so similarly, we can think of the mass term as a self-interaction waves hands, right? I'm skipping over some details, but this is a good picture. Okay, so it's just two fields, and the field, as it's propagating along, is kind of impeded by its own mass, which makes kind of a nice sense when you think of like Newton's inertia, right? Mass is all about making it hard to accelerate or deaccelerate. So as a particle propagates, it's kind of impeded by its own mass. It's a nice picture that works. Don't take it too literally. Okay, so then we will come back to that idea. The standard model is then made up of bosons that have equations that look something like this, a kinetic term and a mass term. And fermions, which have equations which look something like this, which is also a kinetic and a mass term. It just looks a bit different because these are spin half and we have to deal with them. For those who are taking particle physics, the difference here is the Klein-Gordon or Dirac equation. And then all the interaction terms that we want to include. Okay, so then here is the standard model. It's in a very condensed notation. So these capital D's are our derivative terms. So they're all the kinetic terms of the fermions, with I's. We have the G, W, and B lead to bosons. So think of them as the kinetic terms of the bosons, even though the derivatives aren't explicit there. And then down here, we've got the Higgs boson as this phi field. And it's got a nice and explicit double derivative and a mass term, a quantum term. Okay, that's the anatomy of the standard model. In particular, I care about neutrinos, so I care about these three terms in the standard model. Okay, so it involves a kinetic term here and here, two kinetic terms, and it involves this so-called Yukawa term, but it's just an interaction. So the neutrinos are inside this L. This L has two components. There's a neutrino and a left-handed electron field, and then there's a right-handed electron field up there. And notice that the left-handed electron field through that L interacts with the right-handed electron field and the Higgs. Okay. The neutrino does not interact with the Higgs. There's no similar mu right. There's no right-handed neutrino. This is why in the standard model, neutrinos have no mass. Okay. But physics is an experimental science. And so we did experiment. We found out that there must be at least two massive neutrinos. We say at least two massive neutrinos because the experiment we did was neutrino oscillations. And so we've measured a difference in mass between the first and second and the second and third generation of neutrinos. So we would probably assume that all three have mass, but strictly all we know is that at least two have masses. One of these could be zero. And we don't have a measurement of the absolute scale, we just know the relative masses. We do know, however, that they're very small, partly because we didn't detect them having mass until relatively recently in the scheme of physics. Okay, so a standard model needs a mass term. what if we just wrote one down? Right? We wrote down the model. Why can't we just write it with the mass term? So in principle, you could. You could write in this new R, just like we have an ER, and it would all work out the same. And you would end up with the so-called Dirac mass term, which is this sort of mass term of itself interacting, if you like, in that sort of picture. The problem with that, though, is that it would give you for reasonable parameters that you put into the model, it would give you a rather large neutrino mass. Okay, so in principle, you could put it and then just have really small parameters, but that would be very strange because they would be abnormally small compared to the rest of the parameters in the model. And so most of high energy physics is based on, is it beautiful? That is not. Right. But there is something cool about neutrinos. They are their own antiparticle, which means that if I take the charge conjugation of a neutrino, I am taking the opposite of zero charge, which is zero charge. And so you can't distinguish a neutrino from an antineutrino. Okay, and these are called Majorana particles, any particle that has this property. So, could we have a Majorana mass term that we can write like this that doesn't involve a right-handed neutrino? Yeah.
Majorana mass term.
A mass term like this that has Majorana particles, as opposed to the mass term from before. I realize there's a few steps I didn't explain. That becomes the mass term. There is a left-handed field and a right-handed field. So that's not a Majorana mass term.
Are they necessarily distinguishable?
Are they necessarily?
Like, I don't know, if they're similar in sort of those fronts, what's different about them? Like, why do we define them as different things?
Oh, in the same way, a scalar field is its own antiparticle. The scalar field is kind of just trivially its own antiparticle. So it's just because you have to have creation and annihilation operators. And so if you a creation operator will create a particle, but it could also annihilate an antiparticle. So
I think I get an understanding.
Wait, really quickly, does that mean annihilating an antiparticle makes a particle?
It doesn't make a particle. The same operator to make a particle
Yeah. Oh, is the same
annihilates
as
an antiparticle.
Okay.
Yes. Okay, so this Majorana mass term. The problem with this mass term, however, is that, remember, these neutrinos are coming in an L field, so really this term is coming from this term. And this term, both of these become the same charge, and so this violates charge conservation. It's the short and dirty answer of that. So that's also a problem. Okay, so clearly this standard model is incomplete, and we need some new physics. So the new physics has to be above this 1 tera electron volt scale, just because that's what our Large Hadron Collider measures to, and we haven't detected any new physics yet. So we do this using effective field theories. So the most natural extension to the standard model is this dimension 5 so-called Weinberg operator. Okay, there's lots of words in that. Basically, it's just a new operator that we write down. It looks like this. We note, however, that it has a dimension of 5, which basically means it has too many of the wrong type of field, and it can't be physical for reasons that would take too long to describe. So all physical terms have to be dimension 4 or less. 4 is a special number because space-time is 4 dimensions. And so we treat it as an effective operation. And it's here where I'm going to go to pictures, because it makes this discussion a lot easier. So what do I mean by an effective interaction? So let's just consider electrons. Okay, in the classical picture, we have two electrons and you shoot them at each other and they're the same charge, they repel and they collide. And so you could draw a diagram that looks like this on the top left. It has electrons coming in, they interact, they go apart. And you could, in principle, have written down a theory that just has electrons interacting in this way. But you would find that that theory has all the problems that this Weinberg operator has, because this is too many fermion fields interacting all at once. So actually, it needs a particle to mediate it. And it turns out that particle is the photon. So this interaction under the hood is actually this interaction on the right-hand side. Okay, so the top one is just a single photon mediating process. And the second one is you get consecutively more complex diagrams, right? But all of them have the same input output. So you can sort of put it in a black box like that. Okay, so that's sort of a picture of an effective vertex. So then if we draw a Weinberg operator like this as an effective vertex, the question is, what goes here? What is the sort of real physics that's happening? And there are many answers to that. One such answer, the answer I'm working on, is so-called the Z model. Okay, so here I have added two new particles to the standard model. This red little h and the blue capital H. The blue capital H is just another copy of the Higgs particle, and the red little h is kind of like that. And then this, so this is the formalism of an effective field theory. What happens is we, at that really high energy of our new particle being higher than that 1 tera-electron volts, we have these, this is the real process that's happening. That Weinberg operator, we've got two L's coming in and two phi's going out. As we step down in the energies, we progressively, the term is, integrate out these new fields. So see, in this second line, this red H has disappeared, and we've just smushed the line together where the red H was. So on this left one, the red H goes away, and it just becomes this diagram. And on the right one, that red H goes away, and we bring that top vertex down to this left side. Okay, and then we do a similar thing on the next step. We integrate out that new Higgs field. Same thing happens. And we end up with this diagram that is effectively an L going in and interacting with itself and giving us another L. And that's going to be our neutrino mass. So it's very much a sketch. I wouldn't take it too literally, but it gives you an idea of what's happening. Okay. So some key points. So to recap, the standard model is made up of bosons and fermions. We have those kinetic and those mass terms and the interactions. And we can think of the mass term as like a self-interaction. The neutrinos don't have that mass term in the standard model. Okay? But in reality, they do. They have some mass. And this mass needs to be really small. So if we include this Majorana mass using this effective field theory approach, we can generate that mass term, and it naturally becomes very small because in that process of integrating out the particles, we pick up factors of 1 over 16 pi squared and factors of 1 over the mass. Which if the mass is big, that becomes very small. And so it suppresses our neutrino mass. Of course, the process of calculating that step down in energy is highly non-trivial. That's been most of my past year. Yeah. Some other things just to finish off. So this sort of stuff is closely tied to leptogenesis, which is about the matter-antimatter asymmetry of the universe. This is another open question in physics, is why do we see more matter than antimatter? Because the standard model would predict that they should be produced in even pairs. And also looking at some new discrete symmetries for lepton flavors. This is just some other ways you can introduce things into the standard model that suppress interactions that we see to be very small. Yes, so that's the research that I've been doing, and that Mikkel's group does very similar things. Charlie, of course, is from Mikkel's group, so if you want to talk to him about something he's doing, it'd be very similar. And Uri is back there too. He's one of Yvonne's students. So thank you.
Don't have any questions?
Yeah.
You were talking about like obviously like the standard model doesn't account for things like neutrino masses and stuff. I guess what I'm trying to figure out is, are you trying to extend the standard model to make that work, or are you trying to find a different theory or idea that's separate from the standard model that kind of takes all the stuff that does work in it over and add new stuff to that, if that makes sense?
Yes. So yes to both of your points.
Oh.
It's just an extension of the standard model,
Yeah.
which is the same as making a new theory, but taking all the stuff from the standard model and adding new stuff to it.
Okay, right.
So yes, it's just an extension of the standard model. What if we added a new particle? See what happens.
Yeah, okay.
Is there anything any sort of experimental lens you would give to an experimentalist to sort of explore your area, or do you think it's too abstract for an experimentalist? Is it just like another hadron collider?
No. So this is a case where we already have the experiment. We have the neutrino mass oscillations. And so that is the data I am gunning for, right? I can choose all my parameters in the high energy theory and crank the handle and calculate what I would expect to observe. And I want that to match up with the neutrino masses. Okay. Then the question becomes, well, how do I know it's not my theory? How do I know it's my theory and not somebody else's theory? Which could be a different theory, but once you crank the handle, it comes down to the same effective result. So that's where this leptogenesis stuff comes in. Because the nice thing about the Weinberg operator is that it has this delta L equals 2, which means it violates lepton number by 2. And so you can also make predictions about lepton asymmetry from it. And so if you can get both of those predictions to match up, which are independent experimental observations, then there's more rigor to the theory.
Why did that like L equals 2 thing occur? Because do neutrinos have no charge, but then it was like a charge violation?
Yeah, so I swept that under the rug. What's real hypercharge is being violated, not electric charge. Hypercharge is electric charge, but with baggage.
Right. So neutrinos have electric charge with some baggage.
Neutrinos have 0 electric charge, but they still have the baggage.
Right. And then it's all like together in one thing that should be
Correct.
reserved. Nice.
So generally, like as I hear what the story is that the standard model theory, right, is backed by these symmetry groups, right? So I'm just wondering, in terms of what modifications or assumptions you can make for an effective theory, is it constrained by the underlying symmetries of the standard model?
Yes, it is. So in fact, this Weinberg operator, because of those symmetries, is the only 5-dimensional operator you can write. So yes.
You said you wanted to add the Majorana mass thing, and that becomes very small. Why is that better than the other one, which just is very small?
Again, this is a philosophical point. It looks nicer. Right? I mean, physics has had a long history of the things that look nicer tend to be right. And that's what we're banking on. I suppose we haven't had an experiment yet that would say that it's one or the other, being the Dirac mass or the Majorana mass. And so I suppose just good science is just exploring all avenues. Because you don't want to have bias and say, oh, well, maybe it's just the easier thing mathematically, so we'll just go with that and then start doing other things with it. Because it may not be that. Covering all bases is what this is.
Just wondering, what are like the pros and cons of like ground unified theory versus effective field theory? Are there like two competing avenues type?
So I wouldn't say they're directly competing. But there is a school of thought that would say every theory is an effective theory. And the idea is that the goal of a theory is to have predictive power. Again, because it's an experimental science, we want to predict something and then observe. And so in the same way, a civil engineer doesn't need to know about bark confinement to build a steel beam that holds up the building, because it's just a whole different scale. And so the argument would go something like, why would you expect there to be one scale? So should every theory then not be an effective field theory? And if that's the case, it doesn't make sense to say, I want a more basic theory, a more fundamental theory, because you just want the theory that's right for your energy. So that's what effective field theories are doing. They're saying, let me write down a theory that is correct for my energy level without having to know the details of what happens above or below that.
Like making it work for where you are rather than from like the very bottom type thing.
Yes, yes, yes.
Nice.
Yes, yeah, just the symmetries of the standard model. Like I know it's, I guess in a sense, like a continuous symmetry. I'm just wondering, is there like a degree of symmetry, right? For a discrete group, we know we have the order of a group, right? But what do we have, I guess, to characterize when you say we know, I guess it's degree of symmetry, because I'll always only see it as U1, U2, cross SU3, whatever.
Yeah. So, sorry, what was the question?
Like discrete groups, we have an order of the group here, right? The size of the.
Yes, yes.
Do we have something like that for these continuous groups?
Yeah. So continuous groups have generators. Think of it dimension of the group. So where they pop up here is, see this, let's go W. So the W is the weak force boson. That B that you see there, that's saying sum over all the generators of the SU2 group, which is the weak force group. And those generators are the Pauli matrices. So yes, we have the dimension of the group. So SU2 is rotations in 2D space. And so you write that with 2 by 2 matrices, right? Sine, cos. Yes, and that defines sort of the size of your group, if you will.
This is a really simple question, but what is flavor? I hear it a lot and I don't know what it means.
It's when we write down a field theory, first thing you should define your symmetry groups, which in the standard model case is SU3 cross SU2 cross U. And you say, okay, write down every term you can that is allowed by those groups. Okay. So it turns out you could write down terms like this that are allowed by those groups. If you can write down these terms, why can't you write down a second copy of those terms? That would also be allowed. A third copy and a fourth copy, and right? So flavor just labels those copies.
Oh, okay.
Okay? It happens that we have measured 3 flavors of fermions. So muon, electron, muon, and tauon. Flavor is just a label for those repeated.
Yeah.
Are there theoretically n flavors? Like, can there be n flavors, like infinitely?
So what happens is as you go to higher flavors, their lifetime gets very rapidly shorter. So like the tauon is already microseconds. So yes, in principle, there could exist higher flavors, but the muon's microseconds. Who knows what the tauon thing is, right? But beyond that, it's like it's not going to have any effect on the universe because it just doesn't exist for any meaningful amount of time. And so then it's an experimental science. If it doesn't have predictive power, we don't care about it.
Last question. Just the Weinberg operator, right? When
Yes.
we extend it to 5D, we get the Weinberg operator. I assume that there's all the other operators as we go up in dimension. Just wondering if that's bounded about by some possibly maximum dimension we could go into.
No, so there is no maximum. So you could keep going and you get lots of operators as you go into higher dimensions. What catches it is that every dimension you go up, you get a factor of 1 over the energy when you come back down. So if we, where was that? This Weinberg operator here, this is lambda. This is dimension 5, so it's 1 more than 4, so it's got a power of 1 on the lambda power of 1 on the bottom. You go to dimension 6, you get lambda squared, and lambda cubed, so on. And remember, that lambda is bigger than 1 tera electron volt. That's a huge number. So that by the time you, like, this is already suppressed. By the time you square that, it's tiny. By the time you go any higher, forget about it.
Very analogous to perturbative expansion.
It is. That's exactly what it is. Yeah.
Yeah, we're good. No, like, course.
Question. How do the findings of your research affect like the world outside of classical physics? Because personally, I'm not a physicist, but then I'm trying to make a connection between everything that you've said and then my degree.
Yes. Yes. No, this is a good question. So, directly, the answer is it doesn't really. Now, indirectly, we don't yet know, but our grandkids probably would, right? And I say that because if you think, I don't know, take something like semiconductors, right? Semiconductors requires knowing about electrons. It requires knowing about quantum theory, right? They're not a classical thing. You have to know about quantum theory. You have to have done Schrodinger equation, right? And all these things, when that was being done, it was like it wasn't at all obvious what it was going to be useful for. Nobody saw semiconductors coming. Right? But now semiconductors control the world, right? Like every bit of technology. And I think this is true in lots of examples if you go back in history for research. The other thing that's kind of cool that I think Brian Cox actually mentioned at one point, I think it was Brian Cox, he said that when you have people who go out and build experiments like the Large Hadron Collider, or maybe they're building specialist satellites to go and measure something, even if they just want to measure some fundamental particle thing, the fact that you have teams of engineers working on these problems, the amount of technology you sort of tangentially develop is just insane. So like Wi-Fi was invented by a couple of Australians because they were doing radio telescope stuff. Microwaves was invented by somebody who was trying to de-thaw rats, I think. So yes, directly it doesn't really, but I think the pursuit of knowledge always has flow-on effects.
Okay. Thank you, James. I'll write his email on the board if you guys have any more questions. But yeah, we might do a 5-minute break just because Clemens is here. So keep it short. Just get time to get up, get a drink, go to the bathroom, get a snack, and then for us to set up the tech. So sweet.
White boy. White boy.
So since we're teams, what I'm going to do, I'll send you.
I'm saying next year.
Oh, you know the next
Bye bye.
Thanks, see ya.
Yeah. Okay, fair enough. Okay. Cool. We're gonna. Let's go.
Hey, yeah, we're gonna like wire for environment. We think this will be this long ago. What is this big documentary? This one, like, you know that like how America Basically trying to basically like pull a
there's a-
like super
this.
super wide.
One in Texas.
Yeah,
Wait.
yeah. So okay, so we're gonna take like
Super collider?
yeah, this super super wide.
There's a glider.
Yeah, it's
Oh, like
yeah,
a big slide and then they're like.
Yeah.
yeah, it's just that like there's a big like
It's like $32 hole in Texas.
Oh, with the argon. Yes.
Yeah, maybe
No, no.
it is.
It was particle
don't
dot.
have
no,
it.
I remember it's that like
I was trying to detect neutrinos.
So,
no, they were doing that specifically to discover the Higgs boson.
Yeah. It was it's supposed to be research.
Yeah, it went over budget and we went over budget and the whole project basically fell apart.
Yeah.
I remember at one point like there's like this whole big debate like about how like just particle physicists they were trying to hack avoidance and all this, and in turn in a professional like this like where they have Steven Weinberg who is like an old like saying he openly say like. Really, the statement he really said is that, well, frankly, I don't think any like particle physicists say that they're like the most important thing in general. And frankly, at my age, I think you have to know those statements.
Yeah.
He actually he said that line. He said that. That's how yeah.
That's so funny.
That's so funny.
Is the pineapple good? One bite is
Sorry.
Turn around and do that.
So good.
I know.
Oh, yeah, they
You cannot ask it to be like I was gonna say you were like using very competitive. No chance of serious.
That's what he meant in that.
You can rub out that scale.
He's a Michael.
I'm a Michael Schmidt fanboy.
Yeah, I'm not too familiar with Yeah, I'm actually very curious as well because I know quite a bit about particle physics and cosmology. Quantum magnetism.
Yeah,
I think
I do anything.
Okay. Actually, Wait till you see this was flat cat going into
He took me out for something week one, and he got it. Did he? Oh, because I was the 1B. So he took me and Julia out for coffee. Really nice of him. When I was first looking at YouTube to go through, I found his his page. I'm like, oh my god, that sounds awesome. This one guy.
He picked his uni based on that.
I didn't pick it based on that, but I was like, that sounds awesome. And then he was my 1B lecturer, and I was like,
Trade you.
How do you get research? Like, how do you decide? Was it uni first?
oh yeah, I was very upset about that. I was so sad. And I was
very widely recommended.
I'm a Queenslander, right? Around state of origin, everyone giving a shit. And I walked into my 1B lecture.
How did you come across him? Like,
and I'm really sad. And I'm looking at Mikhail Schmidt has the origin score from the night before on the board. And I'm talking like this. He goes,
It's one of those things that it's like
once he stays on his and I don't know.
Is it inherently untestable? Like, is it fundamentally untestable?
Ask Josh. It was more Josh that betrayed me. My friend told him.
Find some planetary system that can produce them, or
I think it's mainly second to third years. Because it makes sense. Because,
The problem is, it's not like honest.
Yeah. And to be honest,
Because that's such high energy, nothing
yeah,
is
so people are like,
supposed to be doing.
yes, I think
significantly higher.
It's not so
a lot of third years.
Yeah, if you're not producing a
It's
closed environment where you have to detect radiation that hasn't happened. You're never gonna be
Is there an energy limit we can produce on Earth? Like, is there a quantifiable value?
Yeah.
You can't produce in any size collider, any size anything.
The only course I could think about
I
that
guess would that be a black
would be
hole?
like
Also like
Yeah, that would be
statistics, yeah, which is
If you make it all the way from pure energy, that's not good.
Good comment. Yeah.
it would be recognizable. Yeah.
Breaks down.
Yeah, but say please.
I wonder if there's some energy where it would trigger like a
Variable might scale up. Which
like a fission chain.
Yeah, exactly.
Is that possible? Can you ignite the atmosphere? Like, if they were originally worried about it, like,
Yeah.
I just want to do it again.
Then we'll see.
Someone just inserted an image of Gillian Murphy on very serious.
Yeah.
That definite happened that one.
Done that, Matt?
Well, like, they did it. They did it. That's why they did. They did.
But it was wrong.
So Dennis,
Maybe.
No.
It's maybe it's one of
Is that still a probability that if you just send off a block,
Yeah.
there's a point something?
Well,
But there's also the same probability that, a particle decays and you get a genetic defect that grows wings.
That's true. They don't do
Concerns?
Well,
Yeah.
Dude,
maybe way more. I'm not.
Every time I look at, like conservative expansion or whatever,
Hmm.
always
yeah,
to
I
be
mean, the worst possible definition of it. Really.
Yeah.
But,
But like this is a.
phenomena is
it's
like,
relative.
you do the perturbation thing.
Well, but this is the point, we're not defining it as a perturbation.
That's
We're using it to
everyone
calculate.
had.
Well,
Very.
like that's what I mean. Like the worst possible. Like it says something like to me, it feels like characterizing things which never been.
What do you know?
Which they have attention.
Like, what would be the thing you wanted to say?
Australians.
Like, internet ad though? Like, I can learn.
Yeah, I mean, any that's easier to participate. It's not just, we assume that people don't negligent. Wait. Oh, yeah. We assume that you take a bunch of stuff out. We don't give it time for it. That's the line standard. That's how
I don't think that's what perturbation is.
Perturbation is very strong. I think it.
That's a very loose approximation.
I don't even think it's that bad. It's
You have to, but like a lot of things.
It's not just approximations, like saying certain things can be technically.
Isn't a perturbation just like add something to the system and then do some maths and see how it evolves and then
Ultimately,
make very box
You have
What was the expansive perturbation theory?
But it's like applying a Taylor theory. Like sometimes you just
Yeah, it's very,
so like if you don't, you get no.
very easy.
Apply it, you get the result. You like it.
Yeah.
Oh, whip it out. E equals MC squared, right? Okay.
It's proven.
So
It's like the
full velocity has this gamma factor 3 velocity. So full momentum
I should say that the
has
particle
m
physics
times
is incomprehensible for me because I'm not trained in that.
Oh yeah, so much better. I'm a
Right?
little bit.
So this thing, right? We know that
I've done 1 week
E
of particle
is the
physics.
energy. How does Einstein know that this was the energy?
I've done
Well, it's m.
really too.
I'm
doing particle physics.
Square root of 1 minus v squared.
Very minimal.
Let's expand that.
Yeah.
That's mc squared times by 1. Half plus half v squared v squared. This is m t squared plus half m v squared. Holy shit, that's like kinetic energy. So that must be a mass energy. Don't even worry about what that is.
It's a lie.
But it works, right?
It's beautiful.
It only works if you don't look close enough.
All right.
They don't
Hopefully you
know,
guys all
guys.
rested up, all eaten. There's a lot of food, hopefully. Yeah, no one ate the fruit, as per usual. Okay.
So missing.
Welcome back. My name is Clemens Ulrich. Going to talk about quantum magnetism. And he's a researcher here. So, round of applause for Clemens Ulrich.
Hello to everybody. So complete different topic, solid state physics, and what I'm doing is experiments. So something completely else. But concerning experiments, I do half of the experiments here in-house, just here around the corner, G10 and G11, and downstairs LG43. But the other half is international collaborations at large-scale facilities, like the 20 megawatt research reactor here, Lucas Heights, or a synchrotron. There's one in Melbourne, which is an electron accelerator ring of 300-meter diameter, $250 million investment for the Australian government. Also working with Hamburg, DESY. They have a free electron laser there, which is a 5.6 kilometer long linear accelerator right in the middle of the city of Hamburg. So the target station is 40-meter underground, and the experimental hall is ground level there, so they are shooting it uphill. 1.3 billion euro investment. So yes, partly expensive research. However, quantum magnetism, what is that? First of all, where is magnetism coming from? If you have a solid, if you have a crystal, what causes the magnetism? Iron, for example. What do you think? Is it the electron or is it the inner core of the atom? Where is the magnetism coming from?
Or the nuclear.
Both.
I guess it's
Well, principle both. The electrons have a spin and the inner core has a spin. However, the Bohr magnetron has a factor in it 1 divided by mass. And since the mass of the nucleus is factor 2000 heavier than the electron, or the hydrogen atom 1863 to be precise, the magnetic moment of the core is a factor of 2000 weaker than the electrons. So it's the electrons which give the magnetic moment. What are the typical elements which are magnetic? It's either the transition metal oxides, vanadium, chromium, titanium, but copper, iron, manganese. So that's that sequence of transition metal oxides. They are famous, and the other ones are rare earth elements like dysprosium, neodymium, or the high power strong magnets nowadays are neodymium magnets. So these are the two lines in the periodic table of elements. And now, if you put them into a crystal lattice, they can order, for example, ferromagnetically, all spins up. That's a classical ferromagnet, or antiferromagnet, up, down, up, down. And here's a list of these names of these exchange interactions. The direct exchange, which already exists in the hydrogen molecule, by the way. Super exchange, antiferromagnetic. Double exchange would give ferromagnetism. So these are the classical magnets. But what we are looking at in our group is a bit more complicated structure. For example, the so-called Dioloshinsky-Moria interaction can give a spin canting, like shown here in the first row, like a zigzag chain. This is actually pretty common. This is not rare, this is common. And in most extreme case, that canting can go in one direction only, and then you get a spin cycloid. That's amazing because you can have a left-handed or right-handed spin cycloid. This is actually called breaking the time reversal symmetry. Sounds interesting, isn't it? No, it refers to the Maxwell equations. There's a minus sign in the time derivative, or other way around. If you travel in this direction, you would see the same effect as if you would travel in that direction on the other cycloid. And now, instead of direction, we call it time. So that's what time reversal symmetry means, left-handed or right-handed cycloid. Yeah, how can we realize such a weird spin structure? There's three options. Either we have that Bialoshinsky-Moria interaction, the cross product gives that canting, or, and now it starts to become really interesting, if we have two or three of these listed interactions competing with each other, which happens actually quite often, then the spins might not know what to do anymore. That's called spin frustration. And the third option is called geometrical frustration. Yeah, sorry for erasing that. So if you have a crystal lattice which contains triangles or honeycomb structure, that's actually realized quite often. Kagome lattice, spinel structure, graphene, honeycomb-like. So we place the first spin here and the second spin here, which would be antiferromagnetic. And now, what should this third spin do? Because that's ferromagnetic, parallel, and that's antiferromagnetic. So simply spoken, that third spin doesn't know what to do. That's called geometrical frustration. And that's one of the three options where quantum magnetism starts. So what are the options? One option is all spins point in one direction. Sure. They can point in a circle, which is fancy, but we have a spin cycloid already. It could happen that all the spins point inwards. That would look like a magnetic monopole. There are no magnetic monopoles, as we know. And actually, the rule also holds because far away might be another structure where all the spins point outwards. So there is always a plus and a minus pole. But the amazing thing is that could move around. And if we zoom in with a microscope, we could kind of simulate a magnetic monopole. So if you type in the keyword magnetic monopole in Google, you'll find a dozen of Nature and Science papers on that. So that's a way to simulate magnetic monopoles. Sounds interesting. Yeah, other option is they don't order at all. They remain disordered, even so that there is a strong interaction. Or they could simply freeze in like a spin glass. That's actually really called spin glass or spin liquid phase transition, which is another way of examining fancy quantum effects. So if you have one of these three options for frustration, either competition between these guys or geometrical frustration, you can get a huge number of interesting quantum effects. And that's called quantum magnetism. Okay. My research is experimental physics, and whatever I did in the last years, I always try to pick up something which might lead to an industry product, an application in the end. And here, actually, if you have such a spin cycloid, that would enable multi-ferroic magneto-electric coupling. So have you ever heard the keyword multi-ferroic? So in our case, we couple electric field and magnetic order. Another multiferroic is that you couple strain and electric field. Ever heard of that? Who of you had an piezoelectric in his hands ever? One, yeah. I tell you, all of you had it in your hands at least 10 times per day. And I see that right away, the mobile phone. Because it means you apply an electric field and the crystal responds and shrinks or expands. That's the microphone or the loudspeaker or your earplug. This is realized in everyday's life. And all of you had, I'm sure all of you had that in your hands today a few times. So that's piezoelectric. What we can realize with the spin cycloidal material is coupling of electric field and magnetic field. Professor Scott from Cambridge University predicted that on a data storage device, you could increase the data storage capacity of your hard drive by 5 to 6 orders of magnitude. So which means you could stick it into your bag and you have 100,000 terabyte hard drive in your hands. Can we believe Professor Scott from Cambridge? I think so, because he was formerly Dean of Faculty here in science. So he came from UNSW. So I believe him. So, or direct computation, because now you have 2 bits, the electric bit and the magnetic bit, and they can even be switched. So that opens, and I'll come to that, this opens an entire new class of applications. So this was my introduction about the keyword quantum magnetism. I hope you found that exciting. For the rest of the talk, I did pick up one example from my own research, namely skyrmions. Skyrmion, the word is coming from particle physics, has similarities to the Higgs boson, but it was also observed in condensed matter physics. And that's an analogon to an skyrmion, a dot-like spin structure, here 3-dimensional. That was actually on the cover of a physics magazine about skyrmions. So yes, a skyrmion is a wheel-like spin structure as shown here in the upper corner. It can consist out of, let's say, 100 spins. The color picture is an electron microscope picture of it. It's not a cartoon. So they really look like that. And once they are formed, they arrange each other in an hexagonal lattice, which is the closest 2-dimensional packing. And the amazing thing is, if you integrate over the spin density in plane, as shown here, with this equation with the cross product, you get quantum numbers, integer numbers. They are quantized. So even though you have an object with 100 spins, the entire object has a quantum number. And that makes them extremely robust and extremely stable. So that's a skyrmion. Here is a list of various materials where the effect was shown. You see the size ranges from 3 nanometer up to 100 nanometer, but more important is the temperature. There are 2 materials here that's actually 560 Kelvin, and here almost 300 Kelvin. That's room temperature, and this is important for any sort of industry application.
Oh my God, made it work.
Yeah, so here, that's the material which we have investigated. copper 2, O, selenium O3. Sounds horribly complicated, and in fact it is. But the main ion, magnetic ion, is the copper. So we are looking at the copper spins. The superstructure here is actually the diamond structure. So it's, in the end, it's super complicated, but the starting point is the simple diamond structure. That's the phase diagram. And we have actually, at zero magnetic field, a helical spin arrangement. And if we switch on a small magnetic field, we see the skyrmions. In a single crystal, just in that very narrow temperature field range, and in thin films in a broad range. Yeah. Applications. Racetrack memory device. Now we can also create single isolated skyrmions and move them around. And each skyrmion is like a data bit. If they have a size of like just 10 nanometers, that's a factor of 10 smaller than the domain walls in the current hard drive. And in the area, that's a factor of 100, 10 squared. So which means we can achieve much, much higher packing densities than on a hard drive. So here, people are close to realization of that. We can create them, we can annihilate them, we can move them around with an electric field. We can detect them, all you need. How can we move them? This is actually the anomalous Hall effect, electric field interacting with the spins. But the analog on here is the Magnus effect, wind on a soccer ball. So this is kind of how that works. Here, experimental data where people moved the skyrmions around. So that really works. And in the end, what is discussed is that these objects could be used for quantum computing in the end. So low energy, high density hard drives, spintronics, magnonics, quantum computing, and even neurological computation, brain-like structures. That's under debate at the moment. So, well, I'm happy if they achieve the data hard drive. That would be the first step. But there's quite a lot of discussion about applications. So we did send, so the crystals were grown in New Zealand with my colleague Thilo Senel. And we shipped the crystals to our colleagues in Brookhaven National Lab. They have an electron microscope. And they measured these pictures on our samples. So here, the zebra stripe structure, that's actually the helical structure. So you have a spin helix like that, and then the next, and then the next. So top view looks like a zebra stripe. If you look closer, we have two domains, that one and that one, 90 degrees from each other. And in the upper corner, you see the starting point of skyrmions, quantum dot points and hexagonal arranged. So interesting, sometimes just right in the middle, you see a single skyrmion popping out here in that corner. And then it disappears again. So that entire structure is quite wobbly. I'll skip that. So we did detailed analysis of that. So my research is optical spectroscopy here in G10, G11, but also neutron scattering. And this is UNSW, the Australian Nuclear Science and Technology Organization, and the 20 megawatt research reactor. So no, Australia is not completely nuclear free. There is one research reactor, In comparison to a nuclear power plant, it's actually tiny. Power plant would be 2 gigawatt, factor of 100. That's also the amount of used uranium. It's just 1%. It's small as compared to a nuclear power plant, but for research, highly important. Purpose number one of the reactor is actually medical isotopes for medical applications. That can be only done at a facility like that. And the only nuclear research reactor where that can be done in the neighborhood here is South Africa, Argentina, Canada. So Australia is serving the entire Asian Pacific area with that. America stopped exporting nuclear isotopes since World Trade Center. Yeah. No, but you can't use a military facility, that's clear. And nuclear reactor power plant is not built for that. So Australia is highly important. Second purpose is actually silicon doping, neutron transmutation doping. So if you need a high quality computer chip, you have to dope it. And the ideal way is stick it next to a reactor. It starts capturing neutrons and transfers the atoms in the next neighboring element. This is the most precise and most homogeneous technique. And something like 40% of the computer chips in your mobile phones and laptops worldwide were processed at UNSW. So if you take your mobile phone, there's a pretty high chance that that piece of silicon was once in that reactor. So there's quite a need for that. And number three is us, neutron scattering. Yes, we recycle what's left from over. Neutron is actually a quite interesting particle. It's a particle, we all know that, but it also has wave properties. And we actually use the wave properties of the neutron to do Bragg diffraction. Do you all know what Bragg diffraction is? Okay, a quick reminder. So we have a crystal lattice. The atoms are perfectly arranged and have a perfect distance. And now you shoot a wave onto the crystal. It could be either X-ray or neutron as particle wave. So we have a wave here that gets reflected here, but also here. And under some angles, we get a superposition of waves. Superposition means we get a sharp peak on our detector. And from the distance of these peaks, we can directly determine the distance of the atoms in the material, but also the symmetry and all arrangements. The neutron also has a magnetic spin on top. Now that's interesting. Now we do particle wave diffraction on the nuclear moment of the neutron. Oh God, yeah. But it's simple in the end. This allows us to determine the precise magnetic structure and the material. The structure, the magnetic moment, the spin direction, everything. Think about an antiferromagnet. If you apply an external magnetic field, nothing will happen because they cancel out. So you can't see an antiferromagnet directly, but with neutrons you can. So you get the full magnetic information. This is the neutron guide hall at UNSW. So these are our instruments. And yes, it's big, heavy research. At the very end, there's this gray wall. That's behind that wall is the nuclear reactor. And it delivers the neutrons to the different instruments. So we have 13 instruments running. The data which I'm going to show you were measured here on that machine. It's called small angle neutron scattering. Since the objects are large, that scattering angle is extremely small. And we use a simple trick. Tiny angles, we place the detector at 20 meters distance. So just simple geometry. Why do we place it in a drum? Funny thing is the neutrons actually fly in air. That's why we have these enclosures and interlock systems everywhere, because by accident you could walk through the neutron beam, which is not healthy at all. So air scattering. So to reduce air scattering, it's placed in an vacuum drum. Interesting is another two numbers. We need a wavelength of about 1 angstrom, and the corresponding kinetic energy would give us a speed of the neutrons. And the speed of the neutrons in that experiment is about 100 kilometers an hour. They are really small, really slow. There are experiments where you can literally walk next to them or even catch them in a magnetic bottle for Bose-Einstein condensation. The other funny thing is, yes, we use it as a wave, but it's also a particle with a mass. And after such a long distance of 20 meters, they arrive a centimeter or two lower due to gravity. So, yeah, once again, big headache. Particle plus wave plus magnetic spin all in one. So, that's the crystal. It was grown by Rosanna in New Zealand. It's a beautiful piece of crystal. You see all these facets. We did neutron lower diffraction at ANSTO to confirm the quality of the crystal. I'm not going into detail here, but you see this highly symmetric arrangement of these Bragg peaks. From that, we can determine the symmetry and the atomic distances. So that's what we see with small angle neutron scattering, and this is now entirely the magnetic signal. Helical, we have a spin helix. They are arranged as zebra stripes. And yeah, in mathematical terms, what you see here is the two-dimensional Fourier transform of that. Or in simple words, two sharp spots. And the angle gives us the direction in which the helix points. And the distance, 2 pi over a, gives us the length of one full round of that helix. So we learn a lot from that. Next picture, number B, also helical, but now we have two domains. And finally, the skyrmions have formed 6 sharp peaks, hexagonal superstructure. They are quite wobbly. They can rotate, and in most cases, you end up with a ring structure. And paramagnetic means above the ordering temperature to confirm that they disappear. It's always an important cross-check. So, doing that, we mapped out the phase diagram here. That's the intensity of the Bragg peaks, the helical phase, the skyrmion phase. And in addition, we did squid magnetization measurements. That was done here in-house, LG43 downstairs. That's a $750,000 piece of equipment. According to the company, the most sensitive in this continent. So, yes. Great. And that's actually the phase diagram. It's perfectly complementary. And here the raw data from the squid experiment. Actually, the squid only detects the ferromagnetic moments, and skyrmions are round. They don't have an external moment in that sense. But what you see here is we remove ferromagnetic spins, so we get a dip here. That's where we see the fermions. It's complementary, but cool and easy. We don't need to do highly expensive neutron experiments. So next is I show you the raw data as a kind of a video. It starts from the helical phase. In that case, 2 domains at 90 degrees. So we expect 4 sharp Bragg peaks. And actually, since the crystal is of such good quality, also higher orders. So 8 and so on. Then we enter the fermion phase and then we see 6 peaks. So this is how it looks like. Helical phase becomes weaker and weaker, disappears for a moment, and now the fermion ring shows up. So this is the result. So from the Bragg peaks, we also extracted their distances, which is either the length of a spin helix or the distance between the fermions in that lattice. That's what we have done here. In our case, about 63 nanometer. And we figured out that they actually expand and even converge to infinity before they evaporate and disappear. That's our core result here. So yeah, we did a couple of runs. I skipped that. This is actually the raw data and how we analyzed it. But I wanted to show you that one. I hope the video starts here. Yeah, it starts. So with the electron microscope in Brookhaven, we even took a real-time video that's shown here. So illumination time per point is half a second. It rattles a bit, but this is indeed real time. And I find that super amazing. If you watch carefully, they always change. They always wobble. They always move around. The hexagonal structure rotates. The coexistence of helix and fermions, but sometimes fermions pop out of the helical phase. And what amazes me is, what are we actually talking about? We are talking about the spins of atoms. So an atom is fixed. The atom can't move around. The spin also can't move around, but the entire object moves. That's like a water wave at Coogee Beach. The wave approaches to the beach, but the water molecule just slightly moves up and down. But a water wave can be quite massive. So it's really like that. So the spins are fixed at an atomic position, but the magnetic structure is totally dynamic and can move around. That's, I think, nicely shown in that video. Okay, now it stopped. And now back to applications. That's what I said in the beginning. We can form isolated fermions and move them around and use them as data bits and for low density, low voltage data storage applications. Yep. Okay, I'm not going into detail here. We measured quite a bit in the end. Each frame is actually something like 900 diffraction pattern. So my PhD student wrote a program to analyze all the 10,000 diffraction pattern in one shot. Otherwise, okay, some core results, and here actually some theoretical explanation of this effect. And the key line is here actually the formation of fermions. We have magnetic exchange interaction plus the Lushinsky-Moria interaction plus Zeeman energy coming from the external applied magnetic field plus magnetic anisotropy from every single copper ion in combination with thermal fluctuations. So 5 in total. At the beginning, I told you we need 2 competing interactions to get spin frustration and quantum magnetism. Here we have 5. So yeah, I'm doing the experiments, but Oleg Tretyakov here, that corridor, is doing the theory on skyrmions. So it's quite intense. Yep. So these are actually from other people's simulations about the distance of skyrmions, and they predicted it. We have measured it, and it's in perfect agreement. So the paper is submitted to Nature at the moment. Okay, very quickly, a short chapter here. Our material orders at about 60 Kelvin, which is miles away from industry applications. We need room temperature. So we tried to find a way how we can extend skyrmion stability range and hopefully to high temperatures. So we did tellurium doping, which means we substituted the selenium with tellurium. Tellurium has slightly larger atomic radius. So if you just consider atoms to be tennis balls, larger radius means there's quite an internal pressure. And this internal pressure is huge because it's on the atomic scale. So simply spoken, tellurium doping means we applied internal pressure. So let's see what happens. Yes, indeed, here the Newton data. The skyrmion stability range increases, but unfortunately towards lower temperatures, not to higher temperatures. So we were hoping that we can shift it up, but well, at least quite interesting result, and especially something for theoreticians to think about it. Yeah, and that's the summary of my talk. We confirmed that we have skyrmions. We measured their length scale and how we can manipulate that with temperature and magnetic field. Highly important for industry applications to know that. And we used tellurium doping to change the skyrmion stability range. That's a highly important slide in the end. That's the list of my collaborators. And it's also highly important for you to see. So I showed you quite some expensive and difficult experiments, and that's all teamwork, international collaborations. So here in my group, Jorge, Firos, Joel, and Nick. Theory here in-house, Oleg Tretyakov and Oleg Sushkov, and one of the PhD students. University of Auckland in New Zealand, Thilo Senel and his group, and Hosanna actually did grow the crystals. Would like to mention also Sam Jig, because he did his honor thesis here in-house with Adam Mikulic. And 3 years later, I hired him as postdoc for another 3 years. And now we have a new grant with Thilo. So he moved on the same project to another lab, to Thilo's group. So we are still working together. I'm the second supervisor of him. Yeah, so that's a kind of a career path. Ansto, Elliot Gilbert, Brookhaven. And as mentioned, data not shown here, Center for Free Electron Laser Science in Hamburg, ESI, that 5.6 kilometer long free electron laser underground underneath Hamburg, and also theory, Max Planck Institute in Stuttgart, Germany. So I'm from Germany, and in Germany we would say, if you drink alone, you die alone. But I'm not drinking anymore. Alcohol-free beer, yes. But concerning condensed matter physics, experimental research, that's absolutely true. It's always a collaboration of minimum 10 people. So the authors list on my papers are always 10 plus people. It's always a big international collaboration, and everyone here has a certain qualification and contributed. Crystal growth, unstored neutrons, free electron microscope theory. So it's an entire collaboration. That makes it also quite exciting and interesting. And yeah, a short information for you. So if you decide to stay in research and continue with a PhD thesis, which I would strongly recommend, there are various travel grants for you to go to an overseas collaborator. For example, the German funding agency DAAD sponsors Australian PhD students to go to Germany for half a year. And that's so intense that they even have an office in Sydney. So they are really trying to convince you guys to come to Germany. For other countries, Britain, Japan, US have similar programs. So international collaboration is really supported. Fortunately, I have to say it starts PhD level and up. Okay, and that's what I would like to conclude my talk. Some diffraction pictures, and in the end, comparison with Australian icon here.
Thank you. Any questions?
Bit of a random question because there's no experimental evidence of it. Would you believe that a magnetic monopole is possible or could exist in any way, shape, or form?
That's a question of, I believe.
Yeah, exactly, because there's no experiment.
So far, it was never ever proven. And even with these magnetic monopoles, there's always an antipole somewhere else on the crystal, but they can move freely. So you can really simulate magnetic monopoles, but they're not standalone items. There's a second antipole somewhere else.
Do you think that's fundamental?
Looks like, yeah, but as I'm experimentalist, I believe is a religious statement. So for me, it means go to the lab and check it. So far, there's no proof.
So all phenomena like these exchange-related, interaction-related magnetic phenomena, right? It's all related to the frustration in the lattice structures.
Either geometrical frustration or frustration through the different competing interactions.
Right.
So both are a means of frustration.
Okay. And geometric frustration is actually come from the lattice structure itself.
Directly. Yep. That's pretty common. Graphite is also honeycomb lattice. Not that unusual.
Oh, wait, so you used
Oh, no, I was just following up. It's not very unusual, but it results in very unusual things.
Yeah.
Like that, yeah.
Quantum magnetism.
Yeah. Scomions, are they relatively stable or do they eventually decay and deform into other things?
That's my next paper.
Send us the archive link.
So one thing, so the main phase, the scomions are supposed to be very stable. Actually, we have new data showing that it's not that stable, but if you quench the crystal, which means you cool it super fast, you can kind of freeze in the scomions and they are metastable. So you can generate them by fast cooling. The amazing thing is their lifetime now depends on temperature, and it's from 10 seconds to 10 days.
Wow.
So you have quantum objects at a time scale of hours and days. So found that quite interesting, and we also were working on that quite a bit. That's of course highly important for industry applications to find the right range, because you don't want that your data hard drive is erased after 2 days. That would be stupid. So yeah, quantum objects and quantum spin quantum fluctuations on the time scale of minutes to hours. That's the next puzzle.
What's the maximum temperature you think you've achieved so far? Like I know you said room temperature is the goal.
460. And
Oh, okay. Wow. That's pretty good.
we have that in the lab in form of a thin film. So the next requirement for industry application is thin films, hard drive.
Is that material dependent or is it structure dependent?
Yes. Yeah. Let me go back to the very beginning. It's a long video. Yeah, here it's table 460 Kelvin, which is 160 above room temperature. Yeah, yes, and the other one, iron germanate, is 278 Kelvin. So we have a thin film of that material and it indicates that the phase transition is 390 Kelvin, which is around room temperature. As said, thin films are required for applications.
What do you look for when you're looking for a new material? Like when you sort of jump to the next material, say if you want to achieve a higher temperature, what sort of, are you just experimenting, see what works? Are you looking for a particular structure? Like what is it?
Yes, exactly. Structure,
Yeah.
that's the key word. We need a so-called non-centrosymmetric crystal to get a spin spiral. Centrosymmetric means if you have a cube and an atom in the center, that's perfectly symmetric, but that atom needs to be slightly displaced, non-centrosymmetric, and that's one of the reasons, crystallographic reasons, why we get spin dot structure. So that's the first starting point. We look up in the international tables for crystallography, what are the potential candidates. We need magnetic moment like copper, or here iron, manganese, vanadium, zinc. That's mandatory. And then, yeah, following that up. Some theory groups are actually working on that, predicting such materials with these magnetic properties by using AI, computer models, self-learning to predict. And what they do is they simply calculate the magnetic properties of randomly generated crystal structures, of course, with that target, and then
Working. Like, do they give new materials that?
Yep. And it's just starting. That's a new field in research. But yeah, people at MIT also are doing that. And yeah, it's quite a bit coming out of that.
So I once remember reading, I guess, about material science and high entropy alloys. And I see that quite a lot of the materials, I guess, they'd be very much expected to be very complex structures, just combinatorically. Not really a question, I guess, just an observation. Yeah, it is the goals we expect to come across interesting properties like this as we go on.
It's actually interesting that you mentioned that, though, these high temperature alloys or perovskites for battery research, organic and perovskite-based solar cells, or ionic conductivity, which is again in batteries. It happens quite often that it's the same material. I study the low temperature magnetic structure, and my colleague, for example, strontium iron oxide, I did the magnetism, and Chris Ling at Sydney University on the same sample measured the high temperature ionic conductivity. So it can indeed happen that such a material has different properties. So I'm focused on quantum magnetism, but Chris Ling, battery research, also highly exciting.
To follow up on that, I think typically, I guess, like thermodynamics or statistical physics, right? What one would expect is that these are just, different phases of the guess it's the material undergoes phase transition.
Yep.
Very different parameters. Yeah. Did predictions for this first come from theory or observation?
Well, in that case, in our special case with the fermion distances and the phase transition from helix to fermion, that was theoretically predicted already in 1994. Fermions were first observed by neutron scattering by a friend of mine, Christian Pfleiderer, with neutron scattering in Munich. So 15 years later, and we just right now did the measurement of that scaling behavior. So the predictions are already 25 years old. So this time, other way around. But we managed to perfectly confirm the predictions. Found that quite interesting.
You said you had a these fermions have quantum number. Do you know? Can you say whether that's integer or?
My one has a quantum number of +1. Others have -1, -2, +2, and half quantum number is theoretically predicted. That's called a meron, and that's main topic of Oleg Tredyakov. He's doing the magnetic spin quantum simulations on that, such spin half.
Can you say if there's any sort of conservation requirement? I'm thinking like because these look quite unstable from the videos you were showing. They're sort of popping away. Like, does that have to then pairs or something? Is there some sort of
No, you can create single isolated fermions with a laser pulse. You can annihilate that later on, an high frequency electric pulse. So single isolated fermions exist and they can be even moved. No conservation here. But the quantum number makes them quite robust, topologically protected objects.
Actually, just to follow up on that, when you mentioned quantum numbers, it made me, I guess, realize these are what's it called, pure method of Brad, about winding numbers.
Yep.
And yeah, I guess you already mentioned it about topological stability and
Yep.
like not pure whatever braid, just stuff of Brad. I think the pure mathematicians interested in this. So
Other way around, the Kieber's fermion, Tom's fermion, British scientist, developed that theory first for particle physics, and the theory also has some links to the Higgs boson. When particle is surrounded by other particles kind of following him. But details, Oleg Tredyakov is doing the quantum mechanics on that.
Yeah, we'll go around of applause. Hopefully you guys have enjoyed. I don't know if you're going to run off or not, but if anyone has any more questions, you can quickly ask him before he runs out the door. Thank you for coming. Thank you very much for coming. There will be another academic talk in week 7, Thursday, same time, same place. There's going to be many more people talking. So some people include Julian Berger, Michael Schmidt, Sarah Martel, Dennis Stello, and a few more people. I think it's like 7 or 8 people talking. So it's going to be many more short presentations. So hopefully, I don't know what that's going to be like. So yeah, thank you very much for coming.
That's not really.
Stay the street. Like, slow down. Like
I'm really scared. Oh my god.
People prefer shorter presentations or longer presentations. So I'm going to see that now. I'm going to see it.
Oh, could have no.
Why would you get this?
Yeah, no, it's actually very interesting. Yeah, I mean, it was good timing as well because
Oh my god.
I say this thing, but I don't
sound like my face when he did that.
Oh, yes, I think there is.
Yeah.
Get rid of it. Get rid of it.
That's actually very. Did you do like I don't have much background.
I got it.
Yeah, no.
I'm not thinking
We
straight.
get this thing.
Like free time, like we.
Thank you very much.
Thank you so much. Yeah.
General role. Yes, yes. And.
Oh, there you go.
Well, statistical mechanics.
It's good. I know it's central.
Yes.
This is.
Break.
From what I.